In this video, part 4 of my series Introduction to Simulating Nature, we'll, as mentioned in the previous part, take another quick look at how the measurement process works in the Variational Quantum Eigensolver. Then we'll briefly review the overall workflow once more before I introduce an alternative approach to the VQE. After that comes the main part of this video, where we implement everything in Qiskit and actually run the simulation using a quantum simulator. If you haven't seen the previous 3 parts yet, I really recommend watching them first. If you're only interested in how the Variational Quantum Eigensolver works and not so much in the general motivation behind simulating nature, then I suggest watching part 3 first and then this part. And if you only want to see how everything is implemented in Qiskit, feel free to skip ahead to the coding section of this video. Now I want to explain one more thing, because some of you, especially the physicists, might be wondering how exactly does this measurement process work and how do we actually calculate the energy. I will try to keep it simple. As already mentioned in the previous video, we have the Hamiltonian. The Hamiltonian contains all the information about our system, in this case the H2 molecule, including the kinetic and potential energy and so on. Strictly speaking, the Hamiltonian we are using here does not contain all the information, but only the part that describes the electrons, because the nucleus-nucleus interaction is treated separately. That part is easier to calculate. We simply compute it mathematically with a formula, and it's roughly 0.7 something. I don't remember the exact value. At the end, we will just add that value to the total energy. So what we calculate and minimize here is only the electron interaction energy. That is what is contained in this Hamiltonian. But the Hamiltonian is not written in the language of qubits. Our qubits only understand whether a spin orbital is occupied by an electron or not. So what we do now is translate this Hamiltonian into what is called the fermionic form, where the Hamiltonian is built up using fermionic operators. That means we have operators that say destroy an electron or create an electron in a certain spin orbital. For those who don't know what a fermion is, fermions are one class of particles with certain properties. The other major class of particles are bosons. That is all we need to know for now. Electrons are fermions, and that's why we call it a fermionic Hamiltonian. So now we have this fermionic Hamiltonian, which contains operators that describe whether an electron is created or destroyed in a certain spin orbital. This is something our qubits can represent, because a qubit in state 1 means an electron is present in that spin orbital, and a qubit in state 0 means it's not. From that, we can translate this description into gates that correctly apply the fermionic Hamiltonian to our qubits. What matters is that this process only becomes relevant during the measurement step. Here's what happens. From the fermionic Hamiltonian that we have translated into gates, we get a new Hamiltonian written in qubit form. And that is the final form we need. How exactly we obtain this result is not important here, and I don't know it in detail either, because Qiskit does this conversion for us. The final Hamiltonian has certain coefficients called C0, C1, C2, and a few more. I haven't written out the full Hamiltonian. Along with these coefficients, it contains expectation values of certain measurements in specific bases. So what we get are these fixed coefficients, C0 to Cn, which come directly from the Hamiltonian. And then we need to insert the expectation values that we obtain from measurements in different bases. For example, the basis C1 means we measure qubit 1 in the C basis. The basis C0 and C1 means we measure qubit 0 and qubit 1 in the C basis and multiply their results. The expectation value is then calculated as follows. We perform the same measurement, for example C1, about 1,000 times for example. We look at all the results from those 1,000 measurements and calculate the average value. If, for instance, 500 measurements give 0 and 500 give 1, we would have an expectation value right in the middle, 0.5. To be precise, when we perform a C measurement, the result is usually defined as -1 for 0 and +1 for 1. So if we measure 0 and 1 equally often, half minus 1 and half plus 1, the expected value would be 0. That's just a small technical detail about how a C measurement works. So for each basis that appears in our Hamiltonian, we perform around 1000 measurements in that basis and compute the expected value from those results. Then we insert these expected values into the Hamiltonian. When we've done this for all bases included in the Hamiltonian, we can compute the total energy. And that energy corresponds to the interaction energy of the electrons. Just to make this clear again, the Hamiltonian, written here with these coefficients and individual expected values, is only a simplified version. The full Hamiltonian is a bit longer and includes a few more bases. When we insert all the coefficients and the expected values that we calculated from our measurements, we get a single number, and this number already represents our energy. So once we evaluate this Hamiltonian as written, we directly obtain the energy of the system. And this is the value we then try to minimize using the Variational Quantum Eigensolver, exactly as I described before. Now, if we recall the Variational Quantum Eigensolver process, we vary the parameters, get a new state vector, perform the basis measurements, calculate the Hamiltonian from them, and from that, the energy. We then use the optimizer to determine how we need to change the parameters, whether to increase or decrease them to minimize the energy. The optimizer adjusts the parameters and we repeat this process. We continue doing this until the measured and calculated energy converges toward a certain value. That value, the point of convergence, is our ground state energy. Once we have found it, we can reconstruct our ground state vector from the measurements. Before we move on to the coding part, I want to briefly mention the limitations of the Variational Quantum Eigensolver and also talk about some alternatives. The VQE is a very good and well-established model. It provides a solid balance between the quality of the result and the computational cost, which is why it's currently the most commonly used approach. However, it's not perfect, because in a way, it's still an approximation. It only searches for a minimum within our parameter space, and whether this minimum actually corresponds to the true physical ground state depends on how good our model is. So while it gives very good results, it's not completely exact. There are also other models, such as a quantum phase estimation, QPE. I won't go into detail about how it works, but this method is exact. In short, it explores different possible states. We start from an initial state, iterate away from it, and when we find the correct one, we obtain the exact quantum mechanical result. The downside is that this method is very resource intensive. It requires fault-tolerant quantum computers with many qubits capable of running deep circuits, meaning a large number of operations in sequence. Besides the VQE and quantum phase estimation, there are also many other models. Some of them are similar to VQE using a variational approach as well. One example is the variational quantum deflation method. This method allows us to not only compute the ground state but also the excited states of molecules. That means when energy is supplied to a molecule from the outside, the probability distribution of the electrons changes. They occupy orbitals with higher energy levels. This changes the overall electron configuration, and for that kind of situation we need a different model than the one we discussed so far. The variational quantum deflation approach is one that can handle this case. In addition to these, there are many other methods, both variational and exact ones, that continue to be developed and improved today. Okay, so now we come to the code section and I go through it step by step again. I've divided the whole thing into sections and I go through each section one by one. And we'll execute everything on a simulator and not just calculate it. And at the end, we'll get a result for the energy, meaning the exact value of the electronic energy. Then we'll add the repulsion energy of the atomic nuclei to that, and in this way we'll obtain the total energy of our H2 molecule. Additionally, I also output the ground state vector. This ground state vector consists of 16 basis states namely from 0, 0, 0, 0 to 1, 1, 1, 1. Each basis state has a certain complex amplitude, and from this complex amplitude we can calculate the probability that this state occurs. Alright, so let's begin. First, we import a few libraries again. We need the PySCF driver, which we'll use to essentially build and compute our Hamiltonian. Then we have the active space transformer. I already mentioned this earlier in the theory part. In principle, it allows us to reduce the number of orbitals that we want to use from the chosen basis. In our case, that's actually irrelevant, because we'll end up using all of them anyway, as you'll see later. But I still wanted to include it here because you see it quite often in tutorials. And finally, we have the parity mapper. In our case, we use the parity mapper, which is one particular method for mapping our fermionic Hamiltonian into Pauli operators, so that it can later be represented on qubits. That is what I've mentioned in the theory part as a mapper. Then we define the distance between the two atomic nuclei. I actually had another version of the code where the distance r wasn't fixed, but instead calculated automatically with a for loop that tries different distances until it finds the optimal one. I removed that part to keep the code shorter, because it's not strictly necessary here. But just so you know, that would have been possible. You could simply loop through several values of r, calculate the energy for each, and then pick the one where the molecule is most stable. The optimal distance is 0.74 angstrom. This means the two atomic nuclei are separated by 0.74 angstrom. And for those who don't know, 1 angstrom equals 10 to the power of minus 10 meters. Next, we define the variable driver using the PySCF driver. We specify our molecule by saying we have two hydrogen atoms. The first one is placed at the coordinate 0, 0, 0, and the second one at 0, 0, r. So we have two hydrogen atoms separated by 0.74 angstrom along the z-axis. Of course, we could have placed them along the x or y-axis as well. It doesn't matter physically, but here we chose the z direction. As the basis set, we use the STO3G basis. This will later give us exactly two spatial orbitals, one bonding and one anti-bonding orbital. Then we define our variable problem. When we call driver point run, PySCF uses the molecular geometry and the basis set to compute all 1 and 2 electron integrals. These integrals form the foundation of the Hamilton matrix. So at this point, all the integrals are calculated. What Qiskit nature also does automatically at this stage is convert that conventional Hamiltonian into its fermionic operator form, just like I explained earlier in the theory part. That means we already get the Hamiltonian expressed in terms of creation and annihilation operators. Next, we define the variable est for the active space transformer. We specify 2 electrons and 2 spatial orbitals. Since the STO3G basis already has only 2 orbitals anyway, this line doesn't actually change anything. But I included it so that you can see what it does and so you know how to use it if you ever wanted to restrict the active space in a larger molecule. Then we update our problem by actually applying the active space transformer with est point transform. And finally, we initialize our mapper. We use the parity mapper method here. If I remember correctly, there are 3 different mapping methods in total. To be honest, I don't know the inner workings of each one in detail, but I decided to go with the parity mapper and we store it in the variable mapper. So next we define our ansatz. To do that, we need to import it, and the one we use here is called UCCSD. This ansatz is basically the gold standard for variational quantum eigensolver methods. There are several different ansätze you could use, but this one is very robust against noise, works extremely well in practice, and very rarely gets stuck in local minima. That's why we are using it here. It's also common in variational algorithms like this to start from the Hartree-Fock approximation, or the Hartree-Fock state. That's exactly what we're doing as well, so we'll import the Hartree-Fock circuit. You don't have to start from it. In principle, you could start from a random point somewhere in Hilbert space, but the UCCSD ansatz is not designed to work properly if you begin from a completely random state. I actually tried that once by initializing a random vector, and the results were completely meaningless. However, there are other Ansätze where that's possible. One example is the two local ansatz. Those are not as robust against noise, so they tend to be more error prone, and they often get stuck in local minima. But if you run the optimization several times, you'll usually end up finding the correct solution. For anyone interested, I put the full code on GitHub so you can copy it and play around with it yourself, and experiment a bit with what works and what doesn't. Next, we define the number of particles, which simply tells the algorithm how many electrons we have, and the number of spatial orbitals, which tells it how many orbitals are in the active space. Next, we define our initial state, which in our case is the Hartree-Fock state, and then our ansatz, which is UCCSD. We pass it the number of orbitals, the number of particles, the mapper we're using, and the initial state. Now, what exactly does the UCCSD ansatz do? Essentially, it takes into account how many orbitals and electrons we have, figures out how many qubits are required, and then applies a set of parameterized RY gates to those qubits. First, it prepares the qubits in a superposition, which means it creates the full 16-dimensional Hilbert space spanned by our 4 qubits. Then, within the Hilbert space, it varies the state vector using a series of gates, just as I explained earlier in the theory part. Because we also give it the mapper, the ansatz knows how the fermionic Hamiltonian should be translated into qubit operations. That means it automatically places the correct gates in the circuit so that when we later perform the measurements, we obtain the right expectation values for each Pauli term in the Hamiltonian. In other words, this part, defining and building the UCCSD ansatz, is really the core of the entire variational quantum eigensolver. This is where the full quantum circuit is constructed. Based on how many orbitals and electrons we have, the ansatz generates the necessary qubits and arranges the gates so that we can explore the energy landscape of our molecule. Alright, so next we define our simulator. I'm using the IR simulator, which we need to import first, and also the generate preset path manager, which we'll talk about in a moment. Then we define our backend, which in this case is a simulator, not a real quantum computer. And the IR simulator contains all the information that a real quantum device would have, including things like gate errors and readout noise, and it essentially allows us to simulate how a real quantum computer would behave. And this of course only works for small circuits. Next we have the generate preset path manager, which we store in the variable PM. What this path manager does is it translates our circuit into a form that the backend, in this case the simulator, can actually understand. Right now our circuit is written in a human readable way, but not every quantum backend supports every possible type of gate, so we have to decompose our circuit into the specific set of native gates that the backend is able to execute. Then there's the optimization level, which we can set between 0 and 3. This controls how much the transpiler tries to simplify or reduce our circuit. It aims to minimize the number of gates while keeping the circuit logically equivalent. On a simulator, you can usually go straight to level 3. What happens is that your computer tries to find the most efficient way to run the same circuit with the fewest possible gates, and that can become computationally expensive for large systems. Also at the highest optimization level, the transpiler can sometimes overcompress the circuit, which might actually make it more sensitive to noise when executed on real hardware. So in practice, you always have to balance it. Choose the optimization level that gives you a good trade-off between speed, stability, and noise robustness. And finally, we run the transpiler with ansatz equals pm.run. Now we're getting to the part where we actually combine everything and execute the full process. For that, we first import all the necessary libraries. I go through each of them in a moment. We import VQE, we also import SLSQP, which we won't actually use here, and I'll explain why, and then SPSA, our optimizer. Next, we import the backend estimator V2 and the ground state eigensolver. Then we define shots with 8192, which means that each individual measurement basis is sampled 8192 times. From these repeated measurements, we calculate the expected value of our Hamiltonian. Next, we define our estimator using the backend estimator V2. For the backend, we use the IR simulator, which we defined earlier. So what exactly does the estimator do? It contains the entire logic related to the measurement process. It runs the backend, performs the measurements, and returns the measured expected values. In short, the estimator handles everything related to measuring and evaluating our circuit. Then we define optimizer. We need this because our goal is to find the optimal parameters that minimize the energy and produce the correct ground state vector. Here we use SPSA with a maximum of 200 iterations, meaning the optimizer can update the parameters up to 200 times. I also imported SLSQP, but we're not using it here. That's because I initially tried it, but it didn't give meaningful results. SLSQP is quite sensitive to noise, and I think that's the reason why it didn't work very well. That's why we're using SPSA instead. It's specifically designed to handle noisy environments and tends to find a stable minimum even when the measurements fluctuate. Once we've defined all of that, the ansatz, the optimizer and the estimator, we combine them together using VQE. The VQE itself doesn't add anything new. It simply manages these three components and executes them in the correct order, optimizing the parameters, measuring the energy, and iterating until convergence. So now we have our complete variational quantum eigensolver defined. But we haven't explicitly defined that we want to obtain the ground state energy and the ground state wave function. That's what the ground state eigensolver is for. You can think of the ground state eigensolver as the conductor of the whole process. It executes everything in the correct order and returns in the end the ground state energy. We provide it with the mapper so it knows how to calculate the ground state energy from the Hamiltonian. And we also pass it the VQE, which already contains our ansatz, optimizer and estimator. In other words, everything it needs to perform the calculation. We store this entire process in the variable called solver. Then, to actually execute it, we call res equals solver.solve and we pass in our problem, which in this case is our H2 molecule. So we're basically telling it, this is the system we want to solve, use this VQE setup with this optimizer, estimator and backend, and compute the ground state energy and the ground state wave function for us. Once it finishes, the result is stored in res, and in the next step, we'll extract all the relevant data we need from that result. Now we need to display our results. So we start by reading out the values that we've just calculated. First, we extract the electronic energy, which is the part that our VQE actually computes. Remember, the quantum algorithm only calculates the electronic contribution. That value is stored in our res object. Next, we read out the nuclear repulsion energy, which is calculated classically from the Coulomb repulsion between the two hydrogen nuclei. Then, by adding these two values together, we get the total energy of the H2 molecule. Finally, we print everything, the total energy, the nuclear repulsion, and the electronic energy, so we can see the complete result of our simulation. And now we've reached the final part of the code. All that's left to do is calculate the state vector from the optimized parameters and then display the results. Just to make this clear, the ground state eigensolver doesn't directly give us the full state vector. It only provides the energy values and some additional quantities, including the optimal parameters found by the optimizer. If we want the actual state vector, we still have to compute it explicitly ourselves. So what do we do here? First, we import state vector from Qiskit, so that we can compute the quantum state of our circuit. Next, we retrieve the optimal parameters that were found during the VQE optimization. We store them in feature opt and we get them from res. Then we calculate the state vector. We insert these optimal parameters back into our ansatz, which prepares the qubits according to the optimized configuration. At that point, our circuit is fully defined, and from it we can directly compute the corresponding quantum state, the state vector. We store it in the variable called psi and print it out. In this case, we can still compute the full state vector because the system is very small. For larger systems, this isn't possible anymore. Instead, we estimate the probabilities of each basis state by sampling, meaning we run the circuit many times and reconstruct the state statistically from the measurement outcomes. On a real quantum computer, of course, because our classical computer does not have the computational power to do that. After that, we access all the amplitudes of the state vector using psi-point data. Since our circuit has 4 qubits, the vector consists of 16 amplitudes, one for each basis state. We store them in amps and then calculate for each amplitude the probability of measuring that basis state, by taking the squared magnitude of each complex amplitude. We store these values in props%, and finally we print everything out using a loop. For each basis state we display the bit string, its complex amplitude and the corresponding measurement probability. And at the very end we also visualize the full circuit once again. It's quite large and a bit messy, but it's there for anyone who's interested in seeing the complete structure. So I've just run the code, and at the top you can see the results. We obtain a total energy of minus 1.1364 Hartree, where 1 Hartree corresponds to about 27.2 electron volts. Then we have the nuclear repulsion energy, which is 0.715 Hartree. And finally the electronic energy, which is the value we actually calculated at minus 1.8515 Hartree. I also added, just above in the code, here the results you would get if you calculated this system classically using the full configuration interaction method. As expected, the nuclear repulsion energy is identical. It's purely classical and determined by a simple formula. But we can see a small difference in the electronic energy compared to our VQE result. Overall though, our calculation is accurate to roughly 2 decimal places, which is quite good for such a small simulation. If I run the code multiple times, the result changes slightly. That's because the algorithm isn't fully deterministic and the optimizer introduces some stochastic variation. Below that, I've plotted the state vector. As you can see, most amplitudes are exactly 0, as expected. Only a few basis states actually contribute to the ground state. Further down, we list all basis states along with their complex amplitudes and the corresponding probabilities. We can clearly see that the state 0011, which corresponds to the Hartree-Fock state, has a probability of about 98.62%, which is why the Hartree-Fock approximation works so well. We also see that 0110 has a small but non-negligible probability of 1.37%, and that 0111 shows a probability of around 0.01%. Which physically shouldn't be possible since that would correspond to 3 electrons. That tiny value likely comes from numerical rounding errors in the simulation. And finally, at the very bottom, we can see the full quantum circuit. It's quite hard to read in this view, but if you want to take a closer look, feel free to copy the code from GitHub and run it yourself. Then you can explore the full circuit in detail. I've now run the code once again to show that if you execute it multiple times, you can indeed get slightly different results each time. And with that, we've reached the end of the video. And also the end of this video series, Introduction to Simulating Nature. This series consists of 4 parts in total, so if you haven't seen the previous ones yet, you can check them out in the same playlist. In the Simulating Nature playlist, there will likely be more videos coming soon, where we'll go a bit deeper into the topic, for example trying out different approaches or Ansätze. I hope this gave you a clear overview and a good understanding of what simulating nature means in the context of quantum computing. Thanks a lot for watching, and I hope to see you again soon.